Okay, so this is me going over the inertia and mass worksheet. We did number 1 in class, but I'll go through it again. It says, which of the following statements are true of inertia? There are 3 true statements. Well, the first 3 all start by saying inertia is a force. Inertia is not a force. So we can cross those off pretty quick, so we know those are not. So the next one, inertia, it says all objects with mass have inertia. That is true. If it's got mass, it's going to have inertia. E, a more massive object has more inertia than a less massive object. That one is also true. These are from your notes if you're not sure. Fast-moving objects have more inertia than slow. That one is not true. Speed doesn't have anything to do with it. G, an object would not have any inertia in a gravity-free environment if there is such a place. That is not true either, because if they have mass, they have inertia, and no matter what the gravity is, there's always mass. Inertia is the tendency of all objects to resist a change in motion. Yes, that is the definition of inertia. Inertia is a tendency or a resistance to change. Okay, so number 2, which of the following statements are true of the quantity mass? There are 5 true statements. The mass of an object is dependent upon the value of the acceleration of gravity. No. If it said the weight is, that would be true, but not the mass. We measure mass in kilograms. That's true. Mass depends on how much stuff is present in an object. Yes, that's kind of the definition of mass, how much stuff is present. The mass of an object can change and is dependent on its location. No, the mass will always stay the same. Weight will change. An object would have more mass on Mount Everest than the same object in the middle of Lake Michigan. Nope, always has the same mass no matter where it is. People and Weight Watchers are really concerned about their mass. They're mass watchers. That is true. People that do the Weight Watchers program say they want to lose weight, but they actually want to lose the amount of stuff in them. So that would be their mass. If all other variables are equal, then an object with a greater mass would have a more difficult time accelerating. Yes, if something has a greater mass, it's going to be harder to push or pull or change its direction. H, if all other variables are equal, then it would require less force to stop an object with less mass than to stop an object with more mass. That's also true. It's kind of the opposite of what the one above is. So the green highlighted ones are your 5 true statements. 3, which of the following statements are true of the quantity weight? There are 4. The weight of an object is dependent on the value of the acceleration due to gravity. Yes, the weight of an object is dependent on gravity. That's kind of what that one is saying. That is true. The mass isn't, but the weight is. We were talking about how your weight could be different, will be different if you were on the moon. Weight refers to a force experienced by an object. Yes, that force would be gravity. The weight on the object would be less on the moon than on Earth. True, I just said that. 1/6. A person could reduce their weight significantly by taking an airplane ride to the top of Mount Everest. That's not far enough. That's not going to, significantly is the key there. So that one is not true. The weight of an object can be measured in kilograms. It's usually not. And then the weight of an object is equal to the force of gravity acting upon that object. Yes, it is gravity's action on the mass. And then when a chemistry student places a beaker on a balance and determines it to be 84.3 grams, they have weighed the beaker. That's not really true. Okay, moving on to 4. Imagine a place in space far from all gravitational and frictional influences. Suppose that you visit that place, just suppose, and throw a rock. The rock will gradually stop or continue in motion in the same direction at a constant speed. It is B. It's going to continue because there's no forces to stop or slow it down. just keep going forever. Number 5 is kind of tricky. A 2 kilogram object is moving horizontally with a constant velocity of a positive 4 meters per second. How much net force is required to keep the object moving at this speed and in this direction? Constant velocity is key. So technically, none is required because, I'll abbreviate, no force is needed to keep it moving at a constant velocity. It's just going to keep going. Now, if you wanted to change it to speed it up or slow it down, then it would be required. The constant velocity is the key there. It's not changing. Okay, question 6. Mac and Tosh are arguing in the cafeteria. Mac says if he flings the Jell-O with greater speed, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with? Well, Tosh is correct because inertia depends on mass, not speed. Suppose you're in space in a weightless environment. Would it require a force to set an object in motion that was at rest? Explain. Yes, it would. Because even if it's a weightless environment, it's not a massless environment. The objects still have mass. Requires a force to move a mass. Fred spends most Sunday afternoons at rest on the sofa, watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? Explain. Well, Fred will likely increase his inertia. Well, he'll increase his mass, because he'll be gaining more mass if he's eating lots and not moving, which will increase his inertia. Ben Too Close is being chased through the woods by a bull moose that he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, yet if Ben makes a zigzag pattern through the woods, he will be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia. Okay, so this moose has a large mass, which means it has a large inertia, which means it's hard for it to change direction. So the moose's large mass means it has a large inertia. It's hard for it to change direction. Remember, changing direction is accelerating. Okay. So, let's just look at the mass of these objects. And so, we'll just rank them from smallest to largest with amount of inertia. So, it says mass and velocity. Velocity, we just said, doesn't matter. So, we can kind of cross off the velocity, and we're going to just rank it from mass. So, smallest to largest, smallest mass would be C. And then we'd move to D, and then A, and B. Okay, I hope that's helpful. for you guys.